I have to start with an apology. So, okay, sorry, no, I have to start with thanks. So thank you for inviting me. Thank you. But then it's an apology. So this is stuff that I mean, everything is very old. I mean, this is I'm repeating talk. Sorry, I'm reviewing. What? Sorry, my microphone, of course. It's on. So I'm reviewing a paper that I wrote more or less 15 years ago. And so first of all, many of you have had enough time to read it and forget it. And the truth is that even I had enough time to forget it. So I'm not comfortable with the details. Ask me only easy questions. I really forgot much of what's in the paper, though the paper is right. So I may end up speaking for less than an hour. We'll see, okay? Also, I should say that, so my purpose is to define the Grothendieck-Teichmuller group, explain in what context it is more or less natural. I should say that it's not quite the same Grothendieck-Teichmuller group that Pierre was talking about yesterday. So it's more or less the same, but it's the same equations, but they take values in different places. In other words, everything is happening in a different completion of the Freely group. So this is the pro-unipotent completion. He was talking about the pro-finite completion, and it's a big difference. Anyway, that's what I'm talking about. Before I really start, just a word. So recently I've been doing things that have to do with Freely algebras, other things that have to do with Freely algebras. And I ended up writing a little computer code that does Freely algebra calculations pretty efficiently. So, for example, I can compute the BCH series to degree 22 and write it in a basis. And there are all sorts of things that I can do with that calculator that I think are, well, nice. So basically, if anybody wants to play with me, it's not sort of, you know, a calculator that you pull out of your pocket and punch numbers, right? I mean, you need a programmer next to you if you want to work with it, okay? It's not really ready-made. But if anybody wants to play with it, I'm here for another month. If you have a worthy project, I'll be happy to collaborate, whatever. Okay. Finally, my talk follows a handout, and here it is in full in front of you. There are also paper copies. If you don't have a paper copy, you should get one from the people at the corners, or you're out. There are more here. Let me pass a few, okay? Okay. So let me start. So this is the paper that I follow. This is Dreenfeld on the right. Sorry, this is the Dreenfeld paper that I aim to decipher. So let me explain what I mean by decipher. So in his paper, so these are direct quotes from his paper. These are scans from his paper. It's all wonderful, but extremely hard to understand. It's basically formulas with no explanation of where they came from. So he defines a certain group, GT, and here is the definition. So it's the set of all G's in the free algebra on A and B, which satisfy a bunch of equations which appear to have no motivation whatsoever. And some of these equations, like the last one, 5.15, is even harder to understand. I mean, because really it's an equation written in a different space, and the space where G lives gets mapped via 5 different homomorphisms into that other space, and then the product of 2 of these of those outputs is set equal to the product of 3 of these outputs. And again, where does it come from? Okay. Then there is a composition law, and if you look at the composition law, again, G1 composed with G2 is equal to, and where on earth did this formula come from? Okay. Then the Lie algebra of that group is explained or defined or stated, and again, it doesn't look any better. So my aim is to make it a bit more natural. Furthermore, then he proves a theorem, and the the theorem is the main theorem somehow. The action of that group on a certain space M of k is free and is free and transitive. And again, the proof is very short, very concise, but if you try to read it, at least it took me a good few months to understand. So let me try to make it a bit simpler. But before that, here's an alternative picture of Drinfeld. So, you know, it's on video. He may see it one day. So let me make it completely clear. This is a huge compliment. If you know who Yoda is from Star Wars, he is the Master Jedi. He knows everything. Maybe sometimes he speaks in a language that's a bit hard to understand, but he knows everything, and I mean it. I have no doubt that Drinfeld knew everything that I'm about to talk about. There is no way he could have written his papers without knowing everything that I will be talking about. But he is the Master Jedi, so he writes in a language that's a bit hard to understand. Okay, here's the overall picture. So the overall picture is the full backside of your handout, but only the green, okay? So look only at the pale green stuff, and that's the overall picture, and then the black stuff is the details that go into the green stuff, okay? So the picture is that there is a certain space B, more precisely a certain algebraic structure B, or, well, it's more or less a group, but more precisely it's a groupoid or a category, and it has various things added to it, bells and whistles added to it, various further operations. So it's a rather complicated algebraic structure B, but let me say that it comes from a reasonably natural place in topology, and it leads to reasonably useful results in topology. For example, the construction of a universal finite type invariant. So it's a good space to look at, this space B. Now, that space B is filtered. In fact, any algebra is automatically filtered. Well, sorry, any augmented algebra is automatically filtered, because you can always look at the augmentation ideal and then look at powers of that augmentation ideal, and that defines a filtration. So the moment you stated the algebraic structure, it's automatically filtered, and once it is filtered, you can look at its associated graded. Its associated graded is the space C. Okay? C is equally complicated, an equally complicated gadget, because all the operations that used to live on B induce corresponding operations on C. So C is again a very complicated gadget with the exact same set of operations. Now, as vector spaces, the associated graded space of a filtered space is always isomorphic to the original vector space, even if not canonically. Okay? Oh, maybe there is some condition about the filtration at infinity. Let's ignore that. Okay? But anyway, at least in the finite case, the associated graded is always isomorphic to the original thing, even if not canonically. Now, but you can ask for more. You can ask for an isomorphism that will respect all the operations that are defined on B and on C. Now, such isomorphisms may or may not exist, and I claim that in our case, such isomorphisms that respect all the structure exist. And in fact, there is a big set of such isomorphisms, and this is this set called, oops, sorry, what did I do? This is this set called ASO up here, and you see it's a set, right? It's a bunch of isomorphisms, and they are all bunched together, bundled together to make one big set. And I will argue that an isomorphism between B and C is precisely the thing that Drinfeld calls an associator. So an associator, which Drinfeld defines as an element in some space, really should be thought of as an isomorphism between a certain space and its associated graded. Now, the moment you have, you missed the beginning of my talk. I said I don't know anything. You win infinity zero. The moment you have two spaces and they are isomorphic, the set of isomorphism between them has two transitive group actions, freely transitive group actions acting on it, namely the automorphisms of the left object and the automorphisms of the right object. So the automorphisms of the left object, these things are what Drinfeld calls GT, or the Grothendieck-Teichmuller group, and the automorphisms of the right object are what Drinfeld calls GRT, and it's some sort of a graded version of the Grothendieck-Teichmuller group. It's isomorphic to the Grothendieck-Teichmuller group because, after all, these objects are isomorphic, but not canonically. Okay? It turns out that GRT is actually the more useful group in our context. So I will spend a little more time on GRT than on GT, but both groups arise from the same picture. Now, I should also say that that same picture repeats in many other places. Namely, there are many other topological contexts that lead to algebraic structures, complicated algebraic structures. So in this case, this is braids, but there are versions with tangles. There are versions with two-dimensional knots in R4, and there are various other versions. And all of these versions have associated gradeds, and it's always interesting to ask whether B is isomorphic to C, again, as an algebraic structure, not just as a vector space. It often is, and the isomorphism is often interesting, and in a little bit later I will explain why. And therefore there are many Grothendieck-Teichmuller GT-GRT pairs beyond the pair that Drinfeld originally studied. Many of these pairs have barely been studied, okay, or haven't been studied at all. So, for example, if you look at the work of Alexeyev-Torossian on the Kashiwara-Verne conjecture, then you will find in it a little group that they called KV, and KV is a similar group of automorphisms of a certain algebraic structure that arises when you study two-dimensional knots in R4. Okay, so there are more examples of the same picture. Anyway, let me start with a baby version. So the baby version is the pure braid group, and I think I want to spend a little time talking about the pure braid group itself. So here's black.jpg showing on the screen right now. Let me tell you a few things about the pure braid group. So first of all, what is the pure braid group? So, let me give it a name. So let PBN be the pure braid group on n strands. And what I mean by that is, I think you all know what a braid is. So let me draw a braid. Here's a braid. This braid is not pure. To be pure, the permutation that the braid induces must be the trivial permutation. So let me make it pure by forcing this back here bringing this where it started and bringing this where it started. So here's a pure braid. Okay? Now, really, what I want to look at is the group ring of the pure braid group. So I allow myself formal linear combinations of pure braids, okay, with coefficients in Q. My coefficients will always be in Q, okay? And maybe I should call this I to the 0. And then there is the augmentation ideal, which I will call I to the 1. And the augmentation ideal is simply the collection of all linear combinations of whose sum of coefficients is equal to 0. So it's the collection of all sigma ai sigma I such that the sum of the ai's is equal to 0. Alternatively, it's the subgroup of the group ring, sorry, it's the sub vectors, well, sub ring of the, it's the ideal, sorry, in the group ring generated by differences, one braid minus another one, okay? Now, so the moment we have a group ring and inside it an ideal, we can look at the second power of this ideal, and it's contained in the first power, and we can look at the third power of that ideal, and that's, that defines a filtration on, well, not quite the pure braid group, but the group ring of the pure braid group. So let me fix some integer m, and then define the sort of mth approximation to the pure braid group to be the pure braid group on n strands divided by, sorry, the group ring of the pure braid group on n strands divided by the m plus first power of the ideal. So I essentially mod out by things that look like the product of m plus 1 differences. Okay? Now, the filtration, this filtration descends to here. And of course, it becomes a finite filtration because the m plus first step of the filtration vanishes here. So this is a finitely filtered ring. Now, in addition, we have these BMs form an inverse system. So we have BM minus 1, and it gets a map from B up M, right? So if you have a good approximation, it maps into a worse approximations, and this gets mapped from Bm plus 1 and so on. So now you can set, you can look at the inverse limit of this system, and let me call the inverse limit B hat, and B hat of course maps onto in fact all of these spaces. Okay? So now I told you what the B side is. The B side in the baby example. So the B side is either B up M for some fixed M, or B hat, the inverse limit of all such B up M's. So now let me tell you what the C side is. So the C side, as promised, is just the associated graded of the B side. So there will be several C sides. There will be C up M, and C up M is just GR of B up M. Sorry. And there will be C hat, and C hat is just GR of B hat. And I suppose I want to tell you what these spaces are. Okay? So the degree M piece, or the degree K piece of any of these spaces, so the degree K piece of any of these is either 0 if we are above the place where we chopped off, or, so this is more or less equal. Okay, it's either 0 or it's simply I to the k divided by I to the k plus 1. Right? And I claim that this is the degree k piece of some fixed algebra C. And I think I want to spend a minute describing this algebra for you. So the algebra C, the chalks here have a very low survival rate, whatever. Wait, I think there are more chalks there. So I guess it's low survival when used by rough people. So let me describe what the algebra C is. So the algebra C is the algebra generated by symbols Tij, where these symbols are symmetric. So it's Tij and Tij is equal to Tji, where both I and j are both between 1 and the number of strands n. And my convention will be that if two indices appear in the same equation, they are different. Okay? So I don't need to tell you that I is different from j, because it's automatic in my convention. Except you have to mod out by some relations. And let me tell you what the relations are. So there are two types of relations. There are locality relations, which say that Tij commutes with Tkl. So this is equal to 0. Okay? And it doesn't make the algebra commutative, because remember my convention. It says that Tij commutes with Tkl only if all four indices are different from each other. Okay? And then there is also a relation often called the 4T relation, also often called the Drinfeld-Kono relation, which has to do with when there are only three indices involved. So this is the relation Tij commutes with Tik plus Tjk. I think all of this is already on the handout, is also on the handout. So if my handwriting is a bit rough, you can still read it.
You need Tii is equal 0, no?
No, there is no Tii.
It's a convention.
No, it's by convention.
It's a convention for him.
There is no Tii. The generators are Tij when I is different than j.
It's the same, you can say Ti.
Well, or else you can say Tii is equal to 0. Okay? Anyway, so maybe I should just tell you why this is plausible. Okay? So it's actually not entirely trivial that this is the associated gradient of that. It can be done entirely within group theory, but it's not completely trivial. So let me quickly make it at least plausible. Okay? So the braid group is the group, so you know, a different way of describing the braid group is to say that the braid group is the group generated by generators sigma ij, where sigma ij is the braid that you get by taking the ith strand, letting it move under all strands up to the jth strand, under the j strand and back over the j strand, and then under everything else and back to place. if this is opposite to what the handout says, and the handout is right, and this is wrong. Okay? So essentially, you take one strand, you pull it all the way around one other strand, and let it go back to place. Obviously, there are then relations, but I don't think I want to write the relations. Anyway, so plausibility for why this is the associated graded of that. Oh, sorry, I should have said one other thing. The degree of each Tij is declared to be 1. So now this is a grade, and all on these relations are both homogeneous. So therefore now this is a graded algebra. And my claim is that the degree k piece of this algebra is I to the k modulo I to the k plus 1. And again, the proof is non-trivial, but let me give you at least a plausibility argument. So let me define a map from the degree k piece of C into I to the k modulo I to the k plus 1. It will not be terribly hard to show that the map is well defined, but the effort is in showing that it has an inverse. Okay? The map is defined as follows. So if you have a word here, so product of Ti alpha j alpha, where alpha runs from 1 to k, and I mean it to be an ordered product. Okay? I will map it to the product as alpha goes from 1 to k of sigma I alpha j alpha minus 1, and this is a product in, so this is a generator of the braid group. This is in the group ring of the braid group. This is a product of k differences in the group ring of the braid group. So it's in the augmentation ideal raised to the power k. So this is here, okay? And I regard it modulo things of degree k plus 1. So it remains to show that this map defined here, do I have a name for it? I don't know. Anyway, it remains to show that this map defined here respects these relations. Okay? Let me skip the locality relation, which is relatively easy, and talk directly about the 4T relation. Okay? So first of all, convention, when I draw a crossing with a dot on it, what I mean is replace it by an overcrossing minus an undercrossing. Okay? So consider the following braid. So the braid looks like, well, it has a crossing here. Well, the way I wrote it, so this will be strand number I, this will be strand number J, no, this will be strand number J, this will be strand number K. The way I wrote it is not a pure braid, but let's pretend that you complete it to a pure braid by multiplying by some further braid down at the bottom. Okay? And then let's add a third component, the component I, and this is component number I, okay? And it goes under the whole picture, okay? So now, on the one hand, this braid, or more precisely, this difference of braids, is precisely equal to the thing you get by flipping all of these crossings. Right? If you flip all of these crossings, then the strand I, instead of being under everything, is above everything. And in either case, you can just slide it out. Okay? So if you flip all crossings, you will get a picture like this. And these two are equal, just strictly equal in the pure braid group, in the group ring of the pure braid group. So meaning the difference between the two is equal to 0. Okay? But you can also compute the difference in 4 steps. So I can flip this crossing, and then after flipping this crossing, I can flip this crossing. And after flipping this, I can flip this. And after flipping this, I can flip this. And overall, I have 4 such flips to make. And each such flip is the difference between an overcrossing or an undercrossing. I actually wasn't careful about the signs, so sometimes they come with minus signs. But essentially, I have the sum with signs of 4 different braids, each of which has 2 double points. 1 double point in the center, and another double point at the place that I'm flipping. Okay? But now, a double point is the difference between an over and an under, and this can be written as the difference between having a crossing and not having a crossing. And you can check that the 4 differences that you will thus get are precisely the 4 differences that appear here. Sorry, the 4, so you can check that when you write this as a product of, as a sum of 4 products of sigma minus 1 times another sigma minus 1, these 4 products will be the 4 images of the product of t's that appear here. Okay? Hence, the 4t relation goes to, well, this sum of 4 products, which is in fact equal to 0. So, QED. Okay? I'm missing, of course, many details, but that's the general idea. Yes?
Is your notation on the handout with these horizontal vertical lines, is that similar to
Yes, so let me say a little bit more. So the convention is actually not to write, or my convention is not to write the algebra algebraically, but rather diagrammatically. So, well, just like the braid group can be written as generators modular relations, I can also write the algebra with pictures. Okay? So the pictures will be, well, n vertical lines for the n strands, and Tij will be a horizontal line going from strand I to strand J. So therefore, this picture will represent an element of degree 3 in the algebra C, and it's the product of 3 t's, and in fact 1, 2, 3, 4, 5. So this is the product T. I read stuff from the bottom to the top. So T24 times T35 times T13. Okay? Now, if you compare it to knot theory, there is an obvious analog in the case of knots with very similar relations and a very similar story. Okay? What else did I want to say? What?
On the right-hand side? Because then it doesn't matter if you change the alphas.
Yeah. Sorry. I'm sorry. Okay. Now, what is it good for? Why should I care about isomorphisms going from here to here? Okay, from B to C. So, the wrong answer is to say because it leads to the Grothendieck-Teichmuller group, because I'm trying to explain why I should care about the Grothendieck-Teichmuller group. But here are 2 other answers. So one answer is that it gives you a computational handle or an algebraic handle with which you can solve topological problems. Yes?
May I ask a question? Before you continue. So you got two groups. One is pluripotent completion of braids, and
Yeah.
another this pluripotent exponent of this GK completed. My question is, are they isomorphic as groups still?
Exponent of
isomorph-
GK.
Yeah. C. What is C? C is
C?
exponent of
C
G.
is just the GR of B hat.
Okay, still, my question is, are they isomorphic as groups?
As algebras, you mean? Which? Sorry, B,
Graded,
C hat
yeah,
and
yeah,
B
yeah,
hat?
okay, yes.
Yes, they are isomorphic
Yeah.
as algebras.
And isomorphism is
But there's
not
no
trivial.
group connected to
Does it
C.
depend on any? Is it
They are isomorphic, but not canonically.
not canonical? It depends on associated or.
It depends on.
Okay.
Well, what exactly does it depend on? I don't know. So, I mean, I'm still in the baby example. In the big example, it will depend on an isomorphism will be the same as an associator. In the case of the pure braid group, I don't think anybody ever worked out exactly what is the set of all isomorphisms between C hat and B hat.
Yeah. Okay, this is not known.
Well,
But maybe these are
I don't know what
associated
known means. I don't know that there are
Maybe-
papers
Maybe
about
from the big picture it follows that associated acts on such isomorphism. Or not.
it. No. Again, this is still the pure braid group. This is still the pure braid group. To get associators, I need to also introduce parenthetizations. This will come in a minute.
I see.
Okay? There was another question? Okay. So again, why should I care? So the point is that it gives me a combinatoric. So this is essentially combinatorics. Finite, in fact, if you chop at a finite degree, it's finite combinatorics. Okay? So this gives me a combinatorial handle or an algebraic handle with which I can answer algebraic questions. So for example, you give me a braid and you ask me, is this braid a square? Okay? Or you give me two braids and you ask me, are these two braids conjugate? Well, actually, you could also ask me, are these two braids equal? So one thing I could do is I could compute the image via some isomorphism Z into here. And if the images are different, then the two braids are not equal. Since this is an isomorphism which preserves algebraic, since I'm looking for isomorphisms that preserve algebraic structure, then if I want to check whether one braid is conjugate to another, I can compute their images, and if they're not conjugate here, they will not be conjugate here either. Now, in the case of braids, it's a bit of silly questions, because the braid group is well understood. There are various much simpler algorithms with which you can answer all of these algebraic, all of these topological questions about braids. But remember that this is just a model. So when you make the corresponding picture for tangles or for two-dimensional things in R4, you actually get handles with which you can answer topological questions, provided that these topological questions can be phrased as questions about the algebra. So is one thing conjugate to another? Again, the algebra will be different, more complicated. It will be categories rather than algebras. They will have auxiliary operations. But so long as you can phrase a question algebraically, this gives you a handle for solving it, a combinatorial handle for solving it. So that's one reason. And the other reason is the following. So maybe I'll use a new blackboard. So I have these spaces B and I have these spaces C, and I'm looking for isomorphisms between them. Suppose I found such an isomorphism, and then suppose somebody gave me a linear functional phi on this space. So a linear functional phi which is homogeneous. So phi is supported on some fixed degree. on degree, say, m things. Okay? Now, also remember that B itself maps into B hat. So, I will get a map from B to the base field, the rationals. Okay? And this map will have the property, since it is supported on degree m things, it will have the property, I don't know, let me call this map V. So this map will have the property that V will vanish on I to the m plus 1. So V evaluated on the augmentation ideal to the degree m plus, raised to the m plus first power, I suppose now I'm considering it as starting here, or maybe I should add group ring here. Then it's equal to 0. And if you look at it, this is precise, if you know what finite type invariants are in knot theory, then this is precisely the definition of finite type invariants. This says that V is an invariant of, well, braids, not knots, but it's an invariant that vanishes on any braid which can be written as a product of m plus 1 differences, meaning which has m plus 1 over minus under differences inside it, and that's exactly the definition of finite type invariants. So, and furthermore, you can check that every finite type invariant V arises in this way. So in the language of knot theory, Z is a universal finite type invariant. In our case, it's a universal finite type invariant of braids, but in other cases it will be a universal finite type invariant of knots or tangles or knotted trivalent graphs or whatever else you will be considering. So again, that's the natural place where B comes from. Okay? Good. Let me go back to the
Again,
white.
it's a group algebra of the pure braid group. You wrote QB, no QB.
Sorry, you're right. It's a pure braid.
You don't say anything about the braids themselves.
What?
You speak only about the pure braids.
Here I speak about pure braids. I could switch my language, change my language a bit, and then talk about braids. Okay? Infinity plus 1, 0. Okay. So I think I'm done telling you about the baby example. How do I switch the light off? Okay. Good. So now it's time to talk about the space B in full. Okay, the actual B, not the baby B. Okay? So the space B is rather complicated. It consists of sort of a space and then a bunch of operations acting on it. So let me start by telling you about what the space is. I guess I wrote here the BM version, okay, but there is also a hat version defined in the same way. So let me first tell you what the objects are here. So instead of talking about braids, I will be talking about parenthesized braids. Rather than defining, here are two examples. So what's a parenthesized braid? It's a braid, not necessarily pure, okay, whose strands are parenthesized at the top and at the bottom. And I think it's clear from the image what parenthesizing means, okay? It also note my convention. So my convention is that when I draw a parenthesized braid, I draw the innermost parenthesization by, I indicate the innermost parenthesization by separating the corresponding strands sort of by a minimal amount. And then since the next strand gets multiplied in later, okay, or the bullet corresponding to the next strand in the parenthesization appears to be multiplied in later, then this distance is, basically you can read the parenthesization from the distance scales. Now, this parenthesized braid, for example, as a braid, it's the trivial braid. However, as a parenthesized braid, it's not trivial because it has a different parenthesization at the bottom than at the top. Now, parenthesized braids are not a group, but rather a category whose objects are parenthetizations. And if you have two parenthesized, and the morphisms are parenthesized braids. So if you have two parenthesized braids and the parenthesization at the top of one matches the parenthesization at the bottom of the next, then you can compose them, and composition is stacking them on top of each other. So my PAB, parenthesized braids, form a category. Now let's continue studying the algebraic structure that this PAB has. The next thing that it has is a skeleton functor. So there is a functor from parenthesized braids to parenthesized permutations. And what's a parenthesized permutation? No formal definition. Here's a picture. Well, it's a permutation with parenthesization at the top and at the bottom. Permutation is just a braid in which you no longer care about the difference between over and under. And quite clearly, there is a skeleton functor. The skeleton functor simply tells you ignore all crossings. So map all crossings to transpositions. Okay? So the skeleton functor applied to this morphism gives this morphism. That's the next bit of structure. What else do I have? So I have operators di's, si, box, and sigma. So sigma is not an operator, it's an element. It's sort of a base point, a special element. I will define it in a minute, but let's first talk about the operators. So the operator D0, when acting on a parenthesized braid, will add a new strand, non-interacting strand, on the far left. Okay? The operator D3, acting on a parenthesized braid with two strands, will add a sort of third strand far away on the right. Far just means that it's outermost in the parenthesization. The operator D2 will double strand number 2. So I count at the bottom, strand number 2, 1, 2, 3 is this strand. And then to double it will just mean that you replace it by two parallel strands that do exactly the same thing with innermost parenthesization. Okay? And well, that defines all the D operators. Okay? And then there is an S operator, which I will hardly ever use, but S2 will mean delete strand number 2. So S2 applied to this parenthesized braid will mean you look at strand number 2 and you delete it, you get this answer. Okay? Next, I have to tell you what is sigma. Oh, sorry, I have to tell you what box is, but I think I don't want to. Box is some sort of a doubling operation, a global doubling operation. You take a braid and you make two copies of it. So it's a coproduct. But I will hardly use it, so I don't want to mention it any further. Then I have to tell you about the base point sigma. The base point sigma is simply this parenthesized braid. So there is only one parenthesization on 2 points, on 2 dots, and you just take the positive, and then otherwise it's just the single positive crossing braid. So now the space B is now completely defined. By the way, you can argue that this is not natural. It actually is a little bit more natural than it looks, so the naturality comes in a different context. And also I should say that the more structure you have, in some sense, the better. Because remember that one of my motivations was to solve topological problems using, by finding such isomorphisms Z. But the topological problems have to be, you have to be able to phrase them as algebraic problems. Okay? So now that I have the operation D2, it allows me to turn more topological questions into algebra. So now I can ask myself, given a certain 4-strand braid, are the middle two strands doing the exact same thing? Okay, and that's the same as asking, is it in the image of D2? And if I have an isomorphism from here to here, I might be able to answer it by combinatorial means. Okay? So, okay, I fully understood B, but that automatically means that I fully understand C. Okay, in principle, I don't even have to tell you what C is, because C is just the associated graded of B. So I guess first of all you have to allow formal linear combinations like the group ring. So allow formal linear combinations in B, but only formal linear combinations in which the skeleton of all the things involved is the same. Okay? So, in other words, an element of B or PAB is really a pair. It's a parenthesized permutation, and then a linear combination of braids whose skeleton is that permutation.
Excuse me.
Okay.
Actually, arrows. You missed to explain because I mean arrow. Arrow is always upwards, right?
Yeah, arrows are always upwards. So
Okay,
then
okay.
there's no arrows,
Okay.
really. I mean, they're drawn, but they play no role because they always go up. In tangle theory, it might be different. Okay. So therefore, it makes sense to speak about sort of an augmentation ideal. More precisely, within every set of morphisms, which now all sets of morphisms have allow formal linear combinations. So within every set of morphisms, you can speak about those combinations of morphisms whose sum of coefficients is equal to 0. It makes sense to say to take powers of ideal in a category just as well as in a ring. Okay, so C is a priori fully well defined, and I don't need to even tell you what it is, but I suppose I should. Okay, so what is C, but with less detail? So again, it's a category with some further bells and whistles, some further structure. And a typical element will look like a parenthesized chord diagram. So a parenthesized chord diagram will be a chord diagram just as in the previous picture, except since the skeleton is now not necessarily pure, you might also have a permutation or a reassociation on the skeleton. You allow same skeleton linear combination. You compose two such things by stacking them one on top of each other. When you stack two such things on top of each other, you can slide the chords to the bottom. So you can slide this chord down to here. Well, it flips over, but it remains the same. And you can slide this chord down to the bottom, and it connects now to here. So it goes to this one. Okay? And I fully define PACD, parenthesized chord diagrams, as a category. It's graded by the number of chords. So the morphisms, every morphism group as gradings by the number of chords. You mod out, sorry.
Can you explain the last step again? Is it too fast for me?
So you can slide down chords. When you compose, you can slide down chords, and you slide a chord down by, well, it just slides along the strand. So if you slide this little line here down, it becomes this little line. And then when you slide this chord down, well, it slides to the other, to strand number 3. I mean, really, it's connected from strand number 1 to strand number 3. So when I write it down below, it's this. Okay? This has to be modded out by the same relation as in the pure braid case, and the proof of these relations is the same proof. Now, on that category of parenthesized chord diagrams, there are operations di, si, box, which I will not discuss, and a basis element, a standard basis element, r tilde, which I will discuss. So first of all, what are di and si? So d0 acting on a parenthesized chord diagram just adds a non-interacting chord or strand on the left. Likewise, D3, or in this case D4, will add a fourth strand on the right with parenthetizations the same way as before. I'm just not indicating the parenthetizations here. D2 will mean double strand number 2. Now, if you want to double strand number 2, the chords that used to connect to it don't know where they should connect. And so what you do is you sum over all ways of connecting these chords to the two daughter strands. So if there were 2 chord ends on strand number 2, you will get a sum of 4 possibilities when you apply D2. Okay? Again,
D2
this is
doubling.
D2 means double strand number 2. Now, again, this is not arbitrary. This is forced. Okay? There is a certain hidden claim here. The claim is that the operation D2 on B induces this operation on C. Okay? I had no choice. It's not an arbitrary definition. Okay? There is a similar definition for the S's, and I think I want to skip it. And the next thing I want to talk is about the base point R tilde. The best way to describe R tilde is to first tell you about X and H. So X is the degree 0 parenthesized chord diagram. Well, degree 0 meaning it has no chords. Okay, so it's just a parenthesized permutation, the permutation written over here. H is the degree 1 parenthesized chord diagram, which has a single chord between 2 vertical strands. And by definition, R tilde, the base point on the C side, is X times exp of H over 2, which really means that, well, let me draw it in a very small font here. It means that you draw X, and on top of it you draw an exponential of H. So exponential means in the formal sense, so you take a product of K H's, you get a thing that looks like this, and you take it with coefficient. I guess I'll write the coefficient on the right so that it will not interact with the picture. You'll take it with a coefficient 1 over K factorial because it's exponential, and 2 to the K because I had an over 2 over there. And then I'll sum as K goes from 0, well, to infinity if I'm in the C hat case, or to M if I'm modded out by the degree M things.
This doesn't come from the fact that it's a gradient of B. It's a choice.
No, so this is a choice. So in fact, this is now an added structure on C.
And what
So,
do you get this formula?
where do you get this formula from? It's the only formula that is compatible with the box, with the coproduct, which I didn't define. So in fact, it is forced. If there is an isomorphism, it will have to map sigma to this, but it's a further argument. It's not. It requires work. Okay.
And when you want to go to tangle, you need it.
When you
When
talk
you want
about
to
tangles,
draw the
it
tangle.
becomes a truly genuinely new constraint. So, in other words, when looking at isomorphisms, I'm restricting. I'm kind of by brute force restricting my attention to isomorphisms. Or rather, I'm adding a base point on the left and on the right, and I'm restricting my attention to isomorphisms that fix that base point, that map the base point to the base point. Okay. Now where was I? I think here. Essentially I'm done, right? I told you what B is, I told you what C is. Okay? Now, what's an isomorphism from B to C? In general, to find an isomorphism from one algebraic structure to another, it's enough to define the isomorphism on generators. Okay? And then it will have to satisfy the relations. Whatever. If your algebraic structure is finitely presented, It's enough to define the isomorphism on generators and insist that it will satisfy the relations. So the next thing to do is I have to tell you what are the generators and relations in B and in C. Okay? So it's easy to show that with all the operations that I have, B is generated by just two elements, A and sigma. Okay? So sigma, the picture is here, A, the picture is here. The basic reason is that, well, it's the same reason why, you know, in elementary algebra, once you have the commutative law and the associative law, you can rewrite any parenthesized product into any other parenthesized product in any other order. So this will be the commutative, will be the thing that applies the commutative law, this will be the thing that applies the associative law. More precisely, if you wanted to write a braid that has the sigma somewhere, you know, in which two strands get permuted, you'll just take this sigma and add non-interacting strands on the left using D0 and add non-interacting strands on the right using Dn+1. Okay? And then this will give you braids with the wrong parenthetizations, and then you will be able to reassociate to bring them to the right parenthetizations using A. So if I wanted an isomorphism from B to C, it's enough to tell you what the value of sigma is and what the value of A is. The value of the value of sigma was declared to be R tilde. Okay, so I don't even have to tell you what that is. The value of A is a single element in C. Call it phi, and it's what's called an associator. But now I have to check what relations phi has to satisfy. So in other words, I have to find the relations that A and sigma satisfy. Well, there are a bunch of non-interesting relations written here, and then come the interesting relations. The interesting relations are the pentagon and the hexagon. So the pentagon says that if you take A and add a strand to it on the right, multiply it by A with the middle strand doubled, and then by A with a strand added on the left, you get the same as A with strand number 1 doubled times A with strand number 3 doubled. So, you know, in formulas, this will be D4A times D2A times D0A is equal to D1A times D3A, and that's the so-called pentagon. The hexagon I could describe in similar ways, but allow me to skip it. Okay? So the element phi, which is the image of A, should satisfy relations, the relation corresponding to what I just said, meaning D4 phi, D2 phi, D0 phi is equal to D1 phi, D3 phi. But this relation is now happening on the C side. Okay? And it should also satisfy relations corresponding to the pentagon, to the hexagon relation, and to the more trivial relations, but I think I'll skip these. Okay? Now, well, okay, so I'm done telling you about the, I've just established the theorem, okay, that isomorphisms from B to C are associators. Okay? This is what Drinfeld calls an associator, anything that satisfies these two relations. But now I need to study the automorphisms of B and C. Okay? And again, the automorphisms of C are a little more useful, so let me talk about the automorphisms of C. This is the group GRT. So for this, I have to describe C in terms of generators and relations. Well, the generators turn out to be X, well, the A as before, X and H as before. Okay? So to describe an automorphism of, oh sorry, and then I have to tell you what the relations are. So there are lots of non-interesting relations, and I don't want to speak about them, but then there are the more interesting relations, and they are a pentagon relation, just as in the B side, and then two hexagon relations, not just one. So a degree 0 hexagon relation, in which, so the left-hand side is x with the left strand doubled, so it's d1 of x, and the right-hand side is, well, a similar thing, but with, well, I think the picture just defines it. And then the other hexagon is the relation written here, and with no detail, okay, but let me just say that it's a degree 1 relation. So it involves a single copy of h on each of the terms that appear in it. So therefore, if you wanted to talk about automorphisms of the C side, then such automorphisms will be determined by their values on x and on h. And it's easy to show since r tilde is fixed. What?
On the C side, you have only two generators?
No, I have three,
Oh.
A, X, and H.
So what's the action on A?
Right, but since the automorphisms I'm looking for fix r tilde,
Oh.
it's easy to show that they have to fix X and H,
Okay.
and therefore it's enough to describe
Okay.
such an isomorphism by its image on A.
Okay.
Let's call the image on A capital psi, and then write the formulas that psi has to satisfy. And the formulas are, well, a pentagon, sorry, not psi, gamma. And the formulas are a pentagon, just like on the, just like for associators, but then a 3-term relation coming from the degree 1, the degree 0 hexagon, and then a funny relation written over here, which is simply the translation into symbols of the funny hexagon. And in fact, you can check that these two relations can be combined into a single relation that can be written in this way. And the cost, and this looks almost exactly like the ordinary hexagon, except the cost here that you have to introduce the variable epsilon whose square is equal to 0. So this really has so this relation has two parts, a degree 0 part and a degree 1 part in epsilon, and the degree 0 part is this, and the degree 1 part in epsilon is this. Okay?
And does it remain valid for general epsilon or not?
The relation?
Well, the last relation.
I don't think so.
No, that's it.
Okay. Now, if you look at the, if you compare it with Drinfeld, then these are precisely the equations that Drinfeld writes in a slightly different language, but they're equally ununderstandable in this language, except in this language they came from a natural place. Okay? But they are the exact same equations that Drinfeld writes. Finally, there is the main theorem. The main theorem is that the obvious projection from isomorphisms that work to degree m to isomorphisms that work only to degree m-1 is surjective. Right? Obviously, if you have an isomorphism that works to degree m, it defines an isomorphism up to degree m-1. The question is whether an isomorphism to degree m-1 actually extends to an isomorphism of degree m. That's the same as asking whether an associator defined to degree m-1 can be extended to an associator that is defined to degree m. why should anybody care? So the reason to care is that this means, so if this is really, if the theorem holds, so if this map is surjective, it means that you can actually construct associators. You can write an associator to degree 7. It's guaranteed that it is extends to an associator to degree 8. So you look for the extension in degree 8. It's a finite search in a finite dimensional space. In fact, it amounts to solving linear equations in a finite dimensional space. A solution is guaranteed to exist. So you find it, and then you extend to degree 9, and so on. So this guarantees that you can iteratively construct associators. Also, it's used in various other places. For example, in Furush's theorem, that the pentagon actually implies the hexagon. Okay? Though you know, so far you could not have used Furush's theorem because Furush's theorem is logically later. Okay? Anyway, how do you prove this? So, and by the way, this implies that there exists a rational associator, because since at every point you solve linear equations, you have no reason to go outside of Q. Okay? So there is an associator that involves multiple zeta values. I mean, I salute the multiple zeta value people, but there is also an associator that does not need multiple zeta values. Okay? Now, the proof is, well, by a little bit of algebraic geometry, you switch the problem from a problem on the set of isomorphisms to a problem on the Lie algebra level. So it's enough to show that the Lie algebra of degree m surjects on the Lie algebra of degree m minus 1. Now, which just amounts to saying that it's enough to show that this Lie algebra is itself graded. Because if it was graded, then, and you had an element in degree m minus 1, you could extend it to degree m by adding 0. It's enough to show that all the it's enough to show that all the relations defining GRT are relations which are of degree 0. Okay? So, well, okay, if you look at the relations, then this is, well, then this is a degree 0 relation, this is a degree 0 relation, this is not a degree 0 relation. So the trick is to show that this relation is actually implied by the previous relations. And that's very similar to Furush's result, but in a slightly different context. And it came earlier. And the proof is rather messy, and I think I anyway ran out of time. But basically, you figure out what the error is in that relation. So the error in that relation is what I will call hexagon sub epsilon. And then you find a complicated way to assemble how many such errors, six or so such errors around a big polytope. And then you have one global argument that shows that the sum of these errors is equal to 0 because they assemble together neatly. And on the other hand, so that means that the errors are related to each other. So the error in that last relation satisfies some equation, and then by a little bit of homological algebra, you show that anything that satisfies this equation is in itself 0. And I think that's the end of my talk. And I sort of apologize for barely knowing what I talk about. Also, I completely lied to you. I said I will speak less than an hour, and I spoke more. Yeah.
Can I make a small comment, which relates here to the Bruno's talk? It's a observation due to Tom Markins, not to myself. Let me just 1 minute. I formulate an observation because it relates to talks given. So you define us, you give us a family of categories which you denoted by PAB. A family parameterized by a natural number. So n is what? Is the number of these black dots which are parenthesized. There's an object in this category. And morphisms are given by Braids. In fact, it's better to think, I mean, you can kind of enumerate, right, this black dot, but you ask that morphism preserve this enumeration. So there is an action of the permutation group here. Claim is that one can observe that this family of categories form an opera. Just this is an opera. So you don't need this operator as di, si, it's a part of operatic structures. And therefore, the correct definition of GT is, this is exactly automorphism group of this category as with marks of completion. So you have to fix field, you have to take completion with respect to natural commutation ideal. This is the definition. So all you need, operatic structure.
Yeah, but all that the operatic structure
I can
is
explain it.
DI and SI. No, no.
Yeah, but still, it's by the way,
I
it's an
agree.
important point of view. Let it has consequences.
Yes.
It has implications, so this is not cheap.
So Hatum is not profinite, right? This is pro-unipotent, really.
Yeah, it's pro-unipotent, yes, it's a matter of completion.
Yeah.
Essentially, all you need to add kind of, if it's a group, you have to add powers to a real number. This is what you need really to make it.
Yeah.
Yeah. I agree.
Any other comment or question, or maybe I can make the connection just to what I said yesterday. So there would be inside in the pro-unipotent case the genus 0 tower, okay? So including the arrows. And another common is, isn't it just the free object in the Braids category?
No, this operator is not free because it is generated. I mean, in PAB you have two things. You
PAB
have,
is the free
you have
object
operatic
in the
compositions, but you also have categorical compositions, and it is generated by precisely. The generators are these. So you have these two trivial braid, and then you have these two. And then you observe and using operatic compositions, you generate any element in here. But they satisfy relations. MacLane's theorem tells there are relations for this pentagon and two hexagons.
No, I mean it's
not
free objects in the category of braided categories.
Ah, yes, then yes. Yes, sorry.
And also, of course, the P I had yesterday is A. The
Yeah.
same thing. Okay, P is just A. Or A is P. And F is phi. Or vice versa.
Okay, I propose that we stop here if there's no further question. So let me go again.